Hello all, today we're going to be looking at another way to integrate something that may be a little bit more challenging to integrate. So we've learned U substitution so far. Today we're going to look at integration by parts. As a real quick reminder, I have covered up the formula on this sheet because I want us to actually talk about a Calc 1 concept, which is when we're taking our derivative of something, so in this case our derivative of x times sine of x, we have to use product rule because we have two functions there that are being multiplied. So our function f, which we define as x, and our function g, which we define as sine of x, we're taking f times g prime plus g times f prime. And sometimes you'll have seen this as u and v prime plus v and u prime, really talking about the same thing. So that's a Calc 1 concept. When we are actually asked to undo that, so we're taking our integral of x cosine of x plus sine of x. Well, actually, that's our answer that we just got up here. That's our answer that we just got up here. So when I'm doing my antiderivative of that, I'm just going to end up with x sine of x. Now, in order to kind of do that, if I actually take my integral of each of these things separately, so I take my integral of x cosine of x and my integral of sine of x, I'll end up with this function right here. And what we're actually trying to find is our integral of that whole function, or integral of that whole function. And I can do that by actually subtracting my sine of x because that's not very bad to take my integral of. In fact, I just know that it's going to be negative cosine. So I can actually subtract that over. So that is truly our formula right here for integration by parts, is we define what our f and our g prime is and what we're trying to find. Our g prime should be something that is not too hard to actually find our antiderivative of, because you'll see g is used over here and over here. And our f is something that when we take our derivative of it, it actually simplifies our function more. So in our case, our f was our x right here because our derivative of that was just 1, and that made our integral easier to take the antiderivative of. Okay, so all that being said, that's still the same thing with f and g. We can actually use for u, and this is our v prime, which was just like our g prime in our other example that we had. So in this example, it actually tells us what to do it with, and this example should look kind of familiar here. So I'm going to let this one be my u, and I'm going to let my sine of x actually be my v prime. I'm going to write this u is equal to x, so I'll find my u prime, which is 1, and my v prime is equal to sine of x. So if I go backwards from there and I try to find what v is equal, that's going to be negative cosine of x. So my integral of this whole thing is actually going to be equal to, well, when I'm doing product rule, I do u times v. So that's kind of what I'm doing here. My u times my v is x times cosine of x. And then usually when we do product rule, we have our function, in this case, our u times our v prime. And so it would be plus that v times our integral of our v times our u prime. But I'm actually going to add that over here and do our integral of, now this is our v times our u prime, because over here it's our u times our v prime. So negative cosine of x times 1, and then this negative and this negative will actually cancel out, and I will get my answer of integral of cosine is going to be just sine, because derivative of sine is cosine. And I have my answer right there, which should be very familiar because that's this example that we looked at right here. Okay, let's take a look at another example that we have here. And first of all, we kind of have to decide what is our u and what is our v prime going to be. And so Our u is usually something that when I take my derivative of it, I'll end up with, something easier. So I'm going to let my u actually be my x. So my u is my x, which means that u prime is just going to be 1. And I'll let my e to the 2x, that whole thing, be my v prime. So now I'm going to have to take my antiderivative of that, which e to the anything, the antiderivative of that is e to the anything. But if I think about doing chain rule, so chain rule going from here to my v prime, I'm going to have to multiply by my derivative of the inside, which is this 2x. So I'll have to multiply by 2, but I want to cancel that out. And so I'm actually going to divide by 1/2. And you could do that with u substitution, but I'm just thinking about this in terms of if I take my derivative here, I'll have to multiply by 2, and that 2 and that 1/2 will cancel out, and I'll just have a 1 out in front. Okay, so now this is all set up. So this thing is going to be equal to what my u times my v is. So I have 1/2 x e to the 2x. When I multiply those, I just put the 1/2 out in front. And then minus my integral of, and then now I'm going to multiply my 1 times my 1/2 e to the 2x, or my v times my u prime, which is the opposite of up here I have u times v prime, so now I'm doing v times u prime. So 1/2 e to the 2x dx. And I technically could definitely use u substitution on this last part, but I might just cheese it because of what we know about when we're taking our antiderivative of e to the anything. So I'm going to just bring my 1/2 out in front. The antiderivative of e to the anything is e to that anything. And then if we think about taking our derivative of e to the 2x, I'm going to multiply by 2 again. So taking my antiderivative, I'm going to do the opposite and divide by 2, which I could have done that with u substitution, but I was just trying to cheat the system a little bit. We can't forget about our plus c. And I think the only thing that we can actually combine here is that 1/2 times that 1/2. That is our final answer. Let's take a look at this next integral that we have here. And this might be a little bit tricky to pick our u and our v. Let's see, if I pick this one as my u, then derivative of ln of x is just 1 over x. But if I pick it as my v prime, then I'm going to have to find what function I can take my derivative and end up with ln of x, which I know that's on our formula sheet, but we're going to pretend like we don't know that. So I am going to pick this one as my u. So I'm going to let u be equal to ln of x, so that I know that my u prime is 1 over x. And I'm going to let this is technically a 1 over x to the third. That is going to be my v prime. So my v prime is on the denominator there. My v prime is 1 over x to the third, or I'll just write it as x to the negative 3. And I'm taking my antiderivative of x to the negative 3. So v is equal to, I'm going to add 1 to my exponent, x to the negative 2, and then divide by that new exponent right there. Cool. So when I'm finding this integral, I'm going to take my u times my v, which now I'm not going to have an ln inside of my integral. So that's good news. So ln times negative 1/2 x to the negative 2, which I could just write as 1 over x squared, minus, and then here's my integral of, instead of u, and then this is my v prime right here, I'm going to do v times u prime. And so I'll have negative 1/2, that's a 2, x to the negative 2 times 1 over x dx. And if we start to simplify that out, first of all, I have 2 negatives. That's going to be a positive. I'm just going to write this as my x squared on the denominator right there. And then I have plus, my 1/2 will come out in front of that integral, and this x to the negative 2 is 1 over x squared. If I combine that with my 1 over x, I will get x to the negative 3 or 1 over x to the third, but I'm just going to write it this way so that I can actually take my integral of that, which means I'm adding 1 to it and then dividing by that new exponent. This is the same thing as above, and it looks like my answer is going to be 1/4, -1/4, x to the negative 2, and I'll just bump that x squared down to the denominator, right? Plus c. Dang it, forgot the plus c. Don't forget that plus c, because when I take my derivative of any constant, it's just going to go away. So the c is going to be real important as we're moving. Okay, so again, it feels like we should use this as our u. So our x is our u, and then this as our v prime. But the second we do that, we don't know what our antiderivative of ln of x is. So I'm actually going to switch this. This is going to be my v prime, and this is going to be my u, because that worked out really, really nicely in our other example where we had a 1 over x and then some stuff canceled out when we multiplied them together. So my v prime is actually going to be my x, which means my antiderivative of x is going to be x squared and then times 1/2. Okay, try this on your own. Go ahead and pause the video, multiply it out. We should end up with this whole function, ln of x, as long as our x is positive, times our x squared, minus, I'm going to bring that 1/2 out in front. And if I think about this as being an x squared divided by an x, I'll just get an x in there, and my integral of that is x. And I just moved my x squared in front of the ln of x so that we didn't get those confused with each other. And I did not forget the plus c this time. Sometimes we will actually get to a function where we may need to apply integration of parts more than once. So for example here, I'm going to pick this one as my u and my e to the 3x as my v prime, because I know how to work backwards from this e to the 3x. I know how to take my antiderivative of that. And my function here is actually going to get easier. So when I let that be my u prime is just going to be 2x. So that function is getting easier when I'm actually looking at my integral part of it. E to the 3x, and I take my antiderivative of that. I will have e to the 3x, and then chain rule says I'll multiply by that 3, and I'll need 1/3 out there in front to cancel out that multiplication by 3. Okay, so this whole thing is going to be equal to x squared times 1/3 e to the 3x minus my integral of these two things multiplied. So 1/3 e to the 3x times 2 to the x. And you can already see, okay, it's a little more simplified, except that I still don't know how to do this. There's a multiplication side of the integral, so I'm going to do u substitution one more time. And same kind of thing that I did before, I'm going to let my u be 2x because it's going to get easier when I take my derivative. I'll just have a constant. And then I am going to let v prime equal my e to the 3x. I'm going to move that 2 and that 1/3 just out in front of my integral. And now when I'm taking my antiderivative of e to the 3x, I will still just end up with e to the 3x divided by 3 right there. Okay, let's rewrite this one more. Since my 2 was part of that function, I just pulled the negative 1/3 out in front. And remember, we are going to have to distribute this negative and this 1/3 to everything. So this is my u times my v first off the bat. So I'll have 2x times 1/3 e to the 3x. And then minus my integral of my v times my u prime. Because over here, it was my v prime times my u. So 1/3, again, e to the 3x times 2, and we finally know how to actually do that integral. I just wrote everything kind of the same. I'm going to bring that 1/3 out in front, actually with the 2. right there, and I'm taking my integral of e to the 3x, which is going to be the same thing, but divided by 3, because when I do chain rule, I will want to get rid of this 3. Yay, we just did integration by parts twice, and that's wild. That's a wild, crazy answer. But if I take my derivative of this, I will end up with x squared e to the 3x, which is kind of bizarre. Okay, we have used indefinite integrals, which means that they don't have bounds, and that's where we have our plus c. But this also works for definite integrals or integrals that are defined on a certain x region or bounds. So for example here, if I'm trying to find x cosine of x evaluated from 0 to pi half, so we're thinking about this is a function, we're finding our area that is underneath this curve from 0 to pi halves. I can use integration by parts here. I just have to remember that I'm plugging in pi halves and 0 wherever I see an x after I've taken my integral. So I'm still going to let this one be my u because it'll just be easier when I'm taking my derivative of that. And I'm going to let my cosine of x be my v prime. So antiderivative of cosine is just sine. Derivative of sine is cosine. Now I'm going to actually multiply these out. So I have my v times my u, which is x times sine of x. And you'll see right here that this says it's evaluated from a to b. So this will be evaluated from x equals 0 to x equals pi halves right here, minus, and then my integral, and this is going to be my v times my u prime. Thank goodness my u prime is just 1, because now I'm just taking my integral of sine of x. And this is also evaluated from 0 to pi halves. I like to plug in my 0 and my pi halves all at once, but you could already have plugged them in right here for this step if you'd like to. But I just like to plug them in all at once. So we are going to take the integral, and then I'll start plugging in the 0 and the pi halves. So minus, and then integral of sine is negative cosine, because if I take my derivative of cosine, I get negative sine. I do not want a negative right here. I have a little positive. But these two negatives next to each other are going to actually become a positive, and then I'm still evaluating this from x equals 0 to pi halves. So let's plug in pi halves, and then we will also plug in x equals 0. I kind of plugged it in a weird way, but I did this first part, and then I did the second part, and somehow I ended up with Christmas colors yet again. Sine of pi halves, let's see, that's my y value at pi halves. So that's just going to be 1. Sine of pi halves is 1. So I'll still just have this pi halves in there. This is going to multiply by 0. And then cosine of pi halves, that's my x value at pi halves, which is 90 degrees. And that's also just going to be 0. So I end up just getting pi halves minus, let's see, cosine at 0, my x value, which will be at 1. And I could just leave my answer like this. You could also make that 1 be a 2 over 2 and then combine it. But either one of those answers will work. Okay, y'all, we got 2 more examples here. And I know this feels really tricky because there's just an ln of x right here, but we technically do not know what the antiderivative of ln of x is. So I'm going to treat this ln of x as if it was my u, which means that my v is going to be this invisible 1 that's just in front of it. So my v right here is going to be invisible 1 that's in front of here is actually going to be my v prime. And why we have a 1 there is it's kind of like a placeholder. It's just our coefficient in front of that ln of x. This will all work out, and it'll be kind of amazing. So if our ln of x is our u prime is 1 over x. And if our v prime is 1, then my antiderivative of that is just going to be x. And it seems like, well, things got a little bit funky here, but I actually do this out. So my u times my v is ln of x times x. minus my integral of, wait, x times 1 over x is just going to be 1, which means that when I take my integral of that, I'll have x times ln of x minus x right there. And all of this is evaluated from x is equal to 1 over e to 1. And now I can, for all of my values, and I also plugged in 1 over e in purple for all of these values. Remember, those are being subtracted. And then if we think about our natural log graph right here at 1, my value is 0 because e to the 0 power is always going to equal 1. So this is going to be 0. I still have a negative 1 in there, and I'm going to distribute this negative to each of them. Ln of 1 over e, so I'm going to write that as ln of e to the negative 1 right there, and my ln and my e will actually cancel out, and I'll just get a negative 1. So I have minus 1 over e to the negative 1 right there, and then this negative is also distributed to this negative. I'll have a plus 1 over e, and then it looks like 2 negatives right there, so I'm going to have 2 of those with a minus 1. So 2 of my 1 over e's, and then minus 1. That's my answer. This is kind of getting repetitive, so you're welcome to stop this and start your homework at any time. But if you need this one last example, we can do it. So I am going to let this one be my u, and I'm going to let my e to the negative 2 x be my v prime because I know how to take my antiderivative of that. My u being, or my x being my u means that when I take my derivative of that, I just get 1, and that'll be inside of my integral, making it a little bit easier. My v prime being that e to the negative 2x, I'm taking my antiderivative of that, so e to the negative 2x, and then chain rule, I would actually multiply by negative 2. There's no negative 2 over here, so to cancel that out, I'm going to divide by negative 2. Try this on your own, writing it all out. Try some bit, but now we're just evaluating it from 0 to 1. So I can already plug in this 1 and the 0 to my first part if I'd like to. So I'd have 1/2 times 1 and then e to the negative 2 right there, minus 1/2 times 0, and then that's just all going to be 0 no matter what. E to the 0 is just 1, but it's multiplied by 0. And now I will actually take my integral of this. I'm going to bring my 1/2 that's here out in front. Integral of e to the negative 2x is e to the negative 2x. And then I'm going to divide by that negative 2 out here because chain rule would actually want that to cancel that out. It looks like I have 2 negatives and 1/2 times 1/2, which will be 1/4. And both of those are evaluated from x is equal to 0 to x is equal to 1. Let's plug those in. Careful of is it feels like when we plug in 0 that it's all just going to go away. But here, when I plug in 0, even though my exponent is 0, e to the 0 power is still 1. And that 1/4 also gets multiplied by it into each of those for my parentheses. Those e to the negative 2's can drop down to our denominator and have an e squared. I can actually combine both of these terms as long as they have common denominators, which I can do if I multiply this one on the left-hand side by 2 over 2, because I'll have a 4e squared on the denominator. And I can actually write this as 3/4 e squared, again on the denominator, minus 1/4, and that would be my final answer.